Alright, this is going to be our walkthrough for the homework assignment titled Calculator Derivatives. So we're just going to be using our calculator to do some things that are going to allow us to solve some calculus problems that have applications with derivatives. So we are going to start off here with one about horizontal and vertical tangent lines. And I think we know that anytime we're asked to find horizontal and vertical tangent lines, it means we need a derivative. So we're going to take the derivative of x, ln x using the product rule. So that'll be x times the derivative of ln x. And then plus the derivative of x, which is 1, times the ln x. On the other side, we'll get 3y squared dy dx for the y cubed. And then we'll use product rule on minus xy to get minus x dy dx minus y. We'll gather all the non-dy dx terms to the left, simplifying the x over x to 1. So we have 1 plus ln x plus y. We'll factor out the dy dx here. Oops, not equals there. We're going to factor out the dy dx. dy dx times 3y squared minus x. Now dy dx is equal to 1 plus ln x plus y divided by that 3y squared minus x. So in order to find when this has horizontal tangent lines, the thing that we need to do is we need to set our numerator equal to 0. And to find when it has vertical tangent lines, we need to set our denominator equal to 0. Right, because a slope of 0 is a horizontal line, and so if our derivative is 0, that means the slope of the tangent line is 0. And a vertical line has an undefined slope, so we set the denominator equal to 0 because that's what would make a fraction undefined, is if its denominator is equal to 0. Neither of these have nice little terms we can factor out of them, so we'll just use just the idea of substitution to figure out when both 1 plus ln x plus y is equal to 0 and x ln x equals y cubed minus xy. It's basically just a nonlinear system of equations. And we'll do the same for the 3y squared minus x. So for the horizontal tangent lines, we'll just solve for y, giving us negative 1 minus ln x. And for the vertical tangent lines, we'll solve for x, because that's a little bit easier. We get x is equal to 3y squared. So we need to figure out when y equals negative 1 minus ln x and x ln x equals y cubed minus xy. So we're going to need a new page for this, so we'll just substitute in that negative 1 minus ln x for all of the y's in our original equation. So the x ln x that we started with on the left side of our original equation will remain unchanged. But on the right-hand side, the y cubed will become negative 1 minus ln x cubed. And then the minus xy will become minus x times negative 1 minus ln x. Okay. That just gives us x ln x equals negative 1 minus ln x cubed, and then plus x ln x. And I think we should, right off the bat, be able to see that the x ln x and the x ln x on each side can just subtract away. We end up with 0 is equal to negative 1 minus ln x cubed plus x. Now, looking at that, we may not right off the bat see a solution to it, which is fine. So what we'll do is we'll just graph this function in our graphing calculator and see when it has an x-intercept, because that's what it means to equal 0, right? A function has an x-intercept when it equals 0. Okay? So we'll go into our graphing calculator, we'll just hit y equals, and we'll punch in our equation, which is going to be what we just had, negative 1 minus natural log of x, and then that's being raised to the power of 3, and then plus the x. And when we graph it, we can see that it looks like this. It looks like it's crossing around 1, doesn't look like it's crossing anywhere else. Sometimes it doesn't resolve real well, so if we zoom in, we're hitting zoom option 2, and if you just hit enter, it'll zoom in right where your cursor is flashing. For us, that's at the origin. I think we can see that it sure looks like it's crossing at x equals 1. But to confirm that it is 1, we want to hit the second button and then the trace button. And when we hit second trace, we choose option number 2, which is 0. And it'll say left bound, and you just want to scroll over using the right arrow button until you are fairly close to your x-intercept, but still on the left of it. Right? That's why it says left bound. It wants you to find a left boundary for where it's testing for an x-intercept. So you hit enter. When you do that, it'll say right bound, and you just scroll over using the right arrow key till you're to the right of that x-intercept. You hit enter. It'll say guess, and you hit enter once more, and it does tell us that this x-intercept is 1. So we know that this is true when x is equal to 1. Well, the next thing we have to do is we have to confirm that if we plug 1 into our original equation, we actually get some y values, because it doesn't necessarily mean that our original function is defined at x equals 1. Well, our original function was x, so 1, ln of x, so ln of 1, is equal to y cubed minus x times y. Well, since we know that the natural log of 1 is 0, this just ends up being 0 equals y cubed minus y. And if we factor out the y, we get y times y squared minus 1 equals 0, or y is equal to 0, and y is equal to positive or negative 1. So we have 3 different possibilities. And what we need to do next then is confirm that, confirm which one actually makes the numerator of our derivative equal to 0. Well, the numerator of our derivative was 1 plus ln x plus y. And if the 3 y values we had were y equals 0, y equals 1, and y equals negative 1, then the 3 points we're going to test this at are 1, 0, 1, negative 1, and 1, 1, right? Because we got 3 different y values, 1, negative 1, and 0. So when we test this out, we end up with 1 plus the ln of 1 plus y. Well, the ln of 1 is 0, so this is equal to 1. That does not make the numerator of our derivative 0, so that one does not yield a horizontal tangent line. The second one here, in fact, we're going to have a 1 plus a 0 for all of these, right? Because the ln of 1 is going to be 0 for all 3 of them. And then we're going to subtract the 1 for the y, which gives us 0. So that one does seem to work. And then our last one will be 1 plus 0 plus 1, which is 2. And that one clearly does not work. What we do want to check also real quickly is that our original denominator of our derivative, which was 3y squared minus x, we need to confirm that that does not equal 0 also at the point 1, negative 1. Well, if I plug in 1 for x and I plug in negative 1 for y, I get 3 times negative 1 squared minus 1, which is 3 minus 1, which is 2. Which, that's not a 2, but since we got a 2 and we didn't get a 0, that's a good thing. That means that this is going to work. So we have one horizontal tangent line. And our horizontal tangent line is just y equals that y value of negative 1. So that's half of this problem. The second half is to deal with the vertical tangent lines. So for our vertical tangent lines, we ended up saying that x is equal to 3y squared. Well, if we go and plug that into our original equation, we end up with, which was x ln x to start with, so we end up with 3y squared ln of 3y squared. And then that should be equal to, we originally had y cubed minus xy, so it would be y cubed minus 3y squared times y. And so if we simplify this down a little bit, we end up with 3y squared ln 3y squared is equal to, well, this is y cubed minus 3y cubed, so that'd be a negative 2y cubed. And if I bring that over to the other side, we should end up getting 2y cubed plus 3y squared natural log of 3y squared. And so we should then be able to figure out, using our graphing calculator, what y values make that true. Now we can't plug y values into our graphing calculator, but we can just replace them all with x's in our graphing calculator, and then look for, again, the x-intercept, right? Because we have this equaling 0. So we'll go back to our graphing calculator. We're going to hit zoom and then option 6, just to put it back to its standard window. And then we'll go into y equals, clear out what we already had, and we'll just type in our new equation, which was 2x to the power of 3. And then we're going to add to that 3x squared, and it was then the natural log of 3x squared. And again, we're typing in x's instead of y's, but that's okay. We just want to find when this function equals 0, so we just need to find the x-intercepts here. So looks like there's probably 3 of them. We'll find this one that's way off to the left first. So we'll hit second and then trace and choose option 2 for 0. And we'll just scroll over for a while here until it's going to be a little bit here until our cursor shows back up. There it is. We are now to the left of our x-intercept. So we'll hit enter. We'll scroll to the right of our x-intercept. We'll hit enter. We'll hit enter again. And we end up getting this value of negative 7.816709. So one of our options is going to be x is, well, it's not going to be x, it's going to be y is equal to. So it's going to be y is equal to negative 7.816709. All right, then we'll go back here. I'm going to hit zoom and option 2 for zoom in. I'm going to move my cursor, maybe, very slowly move my cursor over. Very slowly towards the origin so I can see those values a little bit better over there. If I'd thought ahead here, we wouldn't be sitting here moving our cursor over for a minute, but life will go on. Close enough. We'll zoom in around the origin. And now we will do second trace, and we will pick intersect, not intersect, sorry, 0, and 0, there we go. And we will move over here until we are to the left. Ooh. Well, we lost it there. Let's try that again. Move over here until we are to the left. Hit enter. Move over until we are to the right. Hit enter, and hit enter again, which gives us this nice value of negative 0.738495. So we'll go back to here. We'll say y is also equal to negative 0.738495. And we'll go back to our graphing calculator once more and find the next one, which we think might be right here, but we're going to skip over that one. We'll talk about why we do that in a second. And we'll find this other very obvious one, which is 0.4902993. So we have y is equal to that's a negative sign, 0.4902993. And if we go back to our graphing calculator, the reason we're skipping over this point here when x is equal to 0, let's actually go back and zoom in here around that origin point again. Right, it sure looks like it's hitting the x-axis there, but it looks like it's at the point 0, 0. And it's not going to quite get us on there, but if you try to plug in 0 for x into this, to try to get a y value of 0, we end up, as I'm sure you can see, like it's natural log of 3x squared, right? So if you try to take the natural log of 0, that's undefined. So there's no actual x value at 0. And so we're not going to be able to get any other point where this is crossing right over here, right? It's coming up and it's touching the x-axis, except it's not actually touching the x-axis there, right? It's just getting exceptionally close. So there's no other point there. So now we've got these 3 different y values here, and we then need to plug each of them back into our original equation to see if they actually yield us an x value in our original equation. So this is going to be kind of a little bit tedious here, but we'll start with our negative 0.7816709 value. So if I plug that back into my original equation, we end up with x ln x is equal to negative 7.8166709 cubed plus 7.8166709x. And we just need to figure out when that's true. Well, we can solve that by graphing each piece of this and seeing where they intersect. So we'll do that right now. I'm going to hit zoom 6 to just go back to my standard window. I'm going to go back in here, clear out that equation. We're going to do x ln x as one of our functions here. And then our other function that we're going to use is the other side of it, which was negative 7.8166709. And then that's being cubed. And then it was plus 7.816709x. Now we'll graph those 2 functions, and when we graph them, it looks like it's really only graphed one of them. So it doesn't look like there's any intersection point here. I don't even see, like, we're supposed to have a blue graph and a red graph. So the question is, where is our red graph? Well, if we zoom out some, here, let's just zoom out, option 3, and hit enter. We'll zoom out around the origin. No, I still don't see it. So I'm going to continue to zoom out until I can actually see, oh, there's the red graph. Okay, it just wasn't in our window range. So if I zoom out a little bit more, eventually I'm going to get to where these things hopefully intersect. So I'm going to move up closer to where it looks like they're getting closer to intersecting. And tell it to zoom out again. And somewhere across there, it looks like they've certainly intersected now. So I'm going to hit second and then trace. And I'm going to choose option 5 this time, which is intersect. And well, I'm already on the first curve. I'm just going to hit enter. I'm going to scroll a ways to the right until I can see that I'm clearly past where they've intersected. Now my red one is on top of the blue one. I'll hit enter. It'll say guess. I'll hit enter again. And it's going to give me this value of x equals 183.30284. All right. So that gives us x equals 183.30284. And we don't really need to go back and check that in the numerator of our derivative, because we know that that's not going to make the numerator of our derivative 0 also, because we already found all the x values that make the numerator of our derivative 0. So there's one vertical tangent line. Then we'll go and we'll try and find the next one. So our next value that we had here was, I believe it was negative, we'll have to go back and look, negative 0.738495. So we'll plug that in for our y values. So it's going to end up here being x ln x equals, instead of the negative 7.8, it's going to be negative 0.738495 cubed and then it was minus x times y, so it'll become a plus 0.738495x. And so we'll just plug that one into our graphing calculator. That's going to be much easier. We'll zoom back to our standard window here. And I can keep the x, l, and x. I'm just going to need to change this to negative point. What do we have? We had 738.495 being cubed. And we'll do the same thing over here. We'll get rid of the 7 there and just turn this into 738.495x. And we'll graph them. Oh, and it looks like these are intersecting in a much nicer place for us here. We'll zoom in kind of maybe sort of in the middle here, because I can't quite tell if they're intersecting a second time. Looks like they are intersecting 2 times there, right? So when we do that, we'll look for second trace and option 5, which is intersect. And we'll just say enter on the first one. We'll go over here. We'll find the second one. We'll hit enter. And we'll end up getting x is equal to 1.6361237. So let's put that in here. X is equal to 1.636, I forgot what, 1.6361237. So we'll go with that. That looks like it works. Now, we really should be checking these back in the actual, because it looks like there's a second one here, right? We should be checking these in our original denominator of our derivative, so we'll do that here in a second. So as I go back here to find this other intersection point, looks like for that one we get 0.1545753. So the other thing we got here is x equals 0.1545753. So like I said, we should be checking these values in our original denominator, which was x is equal to 3y squared. Right, so if I try to do x is equal to 3y squared for each of these, keeping in mind that this was my y value here, and these are my x values, I think I'm going to see that if I square negative 0.738495, or if I just multiply that by itself, it's going to be, somewhere around like a half, right? Something like that, right? And because if you just take 7/10 and square that, that's 49/100ths, which is right around a half. So it's going to be around a half. And if I multiply something that's about a half by 3, it's certainly not going to be 0.15457 or 45753. It's going to be much closer to this, right? This is the value that's actually working here. This one doesn't satisfy the original denominator of our derivative, right? So it doesn't actually work. It doesn't actually give us that vertical tangent line. And then we got one more left to do. So our last one was with that y value of 0.4902993. So we'll set x, ln x equal to 0.4902993 cubed minus this time 0.4902993x. And we'll graph that in our graphing calculator. So we'll keep the x, ln x, and now we're going to do 0.4902993, and it's going to become a minus 0.4902993x, and we'll graph it. And it looks like this one only intersects one time, which is nice. So we'll do second trace, and we'll do calculate intersect option 5. I always like to make sure I'm to the left first, even though it doesn't usually matter unless you're looking for multiple intersection points. It might give you the wrong one. Oh, there we go. I didn't mean to go that far, but that's fine. It should still calculate it for us. We end up with 0.7211802. So we end up with x is equal to 0.721, whatever that was, 1802, I believe. And if we plug that one with our y value of 0.90293 back into the original thing there, we could show that that works. In fact, I guess maybe we should do that real quick. We'll do that one on the calculator. The other one was kind of obvious, I think. So for that one, if I do 0.4902993 and square it, and then multiply that by 3, I get that 0.7211802 value. And we could do that with all of them. The 3 that I've boxed here, these 3 most definitely work when you plug them back into x equals 3y squared. And the one extraneous one that we got here definitely does not. So that's the end of the first problem. So it's kind of a time-consuming one there. But now we'll move on to this next one here, where we're looking for just the vertical tangent line to x squared ln xy equals xy squared. So luckily just a vertical tangent line this time, so not as much work to do. We'll take our derivative using the product rule, so it'll be x squared times the derivative of ln of xy. Well, the derivative of ln of xy is 1 over xy times the derivative of xy, which will be x dy dx plus y. And then we'll have to, so this is x squared times the derivative of ln xy, and then we'll have to add to that 2x times ln xy for the second half of the product rule, right? The derivative of x squared times the ln of xy. And then we will say that is equal to product rule on the other one, which is x times the derivative of y squared, which is 2y dy dx. So that'll be 2xy dy dx. And then plus just the y squared, because that's the derivative of x times y squared. So we'll do some simplification here. I'm gonna just do the best I can to simplify this out as quickly as I can. Right? If I'm going to distribute the x squared over x y to the x dy dx and the y, we're going to see the x squared over the x is just an x. And so when I multiply that by x dy dx, we're going to get x squared over y dy dx. And then the y's will cancel when I distribute the next, plus the x's will cancel, so I just end up with a plus x. And then we'll have our plus 2x ln of xy, and we'll have our 2xy dy dx, and our plus y squared. And now we should be able to gather all of our dy dx terms to one side, everything else to the other side, and solve for dy dx. So we will, I guess it doesn't really matter which side. I'll probably, I don't know. Well, actually, what I'll probably do first is I'll probably multiply everything by the y just to clear things up a little bit. So let's call this x squared dy dx. If I multiply the whole left by y, I'm going to get xy here and 2xy ln xy. And on this side, I'm going to get 2xy squared dy dx and a y cubed. Right. So now I've kind of cleaned it up, no more denominators to deal with. And now we'll bring all the dy dx's, let's say, to the left side, I guess. It doesn't really matter. So we'll have x squared minus 2xy squared times the dy dx is equal to y cubed minus xy minus 2xy ln of xy. And our final derivative here will be dy dx is equal to y cubed minus xy minus 2xy ln xy all over x squared minus 2x y squared. And thankfully we're not having to find any horizontal tangent lines here. We just need to work on the vertical tangent lines. So all we really need to do is set our denominator equal to 0 So let's do that. That's x squared minus 2xy squared is equal to 0. We can factor out the x from this to get x minus 2y squared is equal to 0. And that gives us x equals 0 and x is equal to 2y squared. And now immediately from there, we're going to go back and just think about our original equation. Our original equation had natural log of xy. If x is equal to 0, then that would be the natural log of 0. So immediately we can see that that doesn't yield any solutions in our original equation, so we'll just immediately eliminate that. And so then what we'll do is, I think we'll solve this for y this time, even though it's going to give us two different values, a positive and a negative, because then once I've solved it, I've already got my things in terms of x, which is going to allow me to just kind of already have my answers. So if I divide by 2 and then square root, I'm going to get y is equal to positive or negative root x over 2. Okay. So first we'll deal with the negative root x over 2, because that one's kind of easy to deal with. Y is equal to negative root x over 2. Well, if that's the case, and I know x, if that's the case, if y is equal to negative root x over 2, if I plug that into my original equation, right, I end up with x squared ln of x times negative root x over 2 is equal to, I think it was equal to xy squared, right? So equal to x squared over 2 if we do that. If we look at that, we have a little bit of a problem there in that inside that natural log I have x times the negative square root of x over 2. So if x is a positive number, that's my only option here. X is a positive number because otherwise I wouldn't be able to square root it. But if x is a positive number, then inside of here I have a positive number, x, times a negative number here, negative square root of x over 2. So we can see that regardless of the value of x, this provides no solutions in the original equation. And so we can immediately just eliminate y equals negative root x over 2. So we'll go straight to y equals positive root x over 2. And if we do that, if we use y equals positive root x over 2, then we can plug that in and we end up with x squared natural log of x root x over 2 is equal to x squared over 2. And if we go in, we'll just graph each of those separately and look for the point of intersection for them. So here we have our graph. We've got it zoomed at our normal thing here. We'll clear out our old equations from the previous problem. And if we plug in x squared natural log of, we had x square root x over 2. We'll close our parenthesis there. That's our first equation. And then our second equation is just x squared over 2. And if we graph those, it looks like they're for sure intersecting at least once. It's hard to tell what's going on over there at the origin, so we'll zoom in at the origin real quick and we'll come back to that intersection. If I move my cursor away from that, it sure looks like they're intersecting, they're touching each other at 0, 0. We know that y equals x squared over 2. That's the red one, the parabola. It doesn't go below the x-axis, so they're certainly not intersecting below the x-axis. And so the only thing that they could be doing is intersecting really close up there somewhere to the origin. If we zoom in again, right, we can see that like that blue one is not going to go up towards the positive values there. And if you think about the equation itself, right, the x squared natural log of x, times the square root of x over 2, right? I mean, x squared is a positive number, and if I'm taking the natural log of x times root x over 2, I can't imagine that that's going to end up being a negative value. So, and if we look at our table, we can also look at the table in here, right? I guess it does give us some negative values there for the blue one. So, I'm sorry, some positive values for the blue function, right? If we look in there, right, we're getting some positive values for the blue function, but they're not any of them anywhere close to x equals 1. They're all past x equals 1. So we don't really need to worry about those. So if we do our second calculate option 5 intersect for this, we just need to find this one point of intersection. And when we do that, same method as before. Oh, we've gone way too far again. I've lost it. We'll try this again. We end up getting this value of 1.7583615. And we know that that's going to work in our original equation. And if we look back up here to our original equation, with the y value that we had two positive values, and so I should be able to come up with a solution there for those. So I don't really need to do much other work here. We can just go right ahead and say that that should be our solution. Right? That should be our vertical tangent line. And I guess, I mean, what we could do is, since we did get a y value there, we could take our y value that we got and plug that x and that y value in to our original numerator here and make sure it doesn't make it equal to 0. When I made the answer key, I did that. I'm not going to go through just the arithmetic of plugging that in. It doesn't. And so that's our vertical tangent line. All right, so we'll move on to our next one here. This is finding the vertical tangent line of x ln y squared equals x squared y squared. So we'll start off by taking the derivative using the product rule. It would be x times the derivative of natural log of y squared, which will be 1 over y squared, times the derivative of y squared, which will be 2y dy dx. And then we will add to that the derivative of x, which is 1, and then the natural log of y squared, and then we will do the product rule on the other side, which will give us it'll give us a x squared times the derivative of y squared, so that'll be x squared times 2y dy dx, and then plus the derivative of x squared, which is 2x, times the y squared. Again, I think I'm going to just multiply. Well, first I'm going to cancel out this y and this y squared here. So right, I'm just going to end up with a 2x over a y here, and then I'm going to multiply everything by that y in just a second. So we'll write this all out. And when I multiply this all out with the y there, we're going to end up with 2x dy dx plus y ln y squared equals 2x squared y squared dy dx plus 2x y cubed. And I'm not going to write out the two steps here. I'm just going to give us our dy dx. I'll subtract the y ln y squared over to the right-hand side. And when I subtract the 2x squared y squared to the left-hand side and factor it out and divide, I get 2x minus 2x squared y squared. So there's our dy dx. And we are solely interested here in when this thing is having a vertical tangent line. So that means we just need to set the denominator of this equal to 0. So that denominator was 2x minus 2x squared y squared. We set that equal to 0. We can factor out a 2x, which leaves us with 1 minus xy squared is equal to 0, which gives us 2x equals 0, or x equals 0. And it also gives us this 1 minus xy squared is equal to 0. Well, if I look back at my original equation, I can see that I've got a bunch of y squareds in it. It would be really easy to replace the y squareds if I solve for y squared. So if I solve this for y squared, right, that's going to give me xy squared equals 1, or y squared equals 1 over x. So if I plug y squared equals 1 over x back into my original equation up here, right? So the y squareds are just going to be 1 over x's. I'm going to get, right, this is into the original. We're going to get our x, ln y squared will be ln 1 over x. And then it's going to equal, it was x squared times y squared, so that'll be x squared times 1 over x. So we end up with x ln 1 over x is equal to x. Well, if I just divide both sides of that by x, we end up with ln 1 over x is equal to 1. And if I then exponentiate both sides of that, we're kind of running out of room here, right? We end up with e to the ln of 1 over x is equal to e to the first power. Or we end up with, just since e to the ln of 1 over x is just 1 over x, we end up with 1 over x is equal to e, or x is equal to 1 over e. So we end up with these two values, x equals 0 and x equals 1 over e. Now, if we go back to our original equation and we plug in 0 to it, I think we can see that if you plug in 0 to that original equation, you just get 0 equals 0. So we know that's true. And that means that if we should check in the numerator, but if I plug in 0 into the numerator of our derivative, just to make sure it doesn't also make it 0, we'll end up with negative y ln y squared. So as long as y isn't 0, then that should work. And y can't be 0 because then we'd be taking the natural log of 0. So we know that x equals 0 is a vertical tangent line. So that's good. And if we look at x equals 1 over e back in our original equation, let's see here, we'll make a new page for this new equation. All right, so if we've got x is equal to 1 over e, then we end up with 1 over e natural log of y squared is equal to 1 over e squared y squared. And so as long as those have an intersection point and that intersection point doesn't make the numerator of our original derivative 0, then we should have that as a vertical tangent line as well. We can real quickly check that here on our graph. We'll zoom back to our standard by hitting zoom 6. Let's see, I do need to, so let's see, we had 1, we'll put it here, we had 1 over e times the natural log of y squared. So I'm just going to use the fraction button here and say it's natural log, and we have to use x, right? Natural log of x squared over e as one graph, and then the other graph was x squared. I should have put that in the nice little fraction form, but that's fine. It's x squared over e squared. And when we graph those, we can see that it sure does look like there are some intersection points there. And if we go in and we look for the intersection point, looks like we end up getting that happens at 1.6487208. And I think we should be able to tell that those are positive or negative of that value, right, because those are both even functions that we're looking at there. So they should be symmetric across the y-axis. They certainly look symmetric across the y-axis, and they definitely are symmetric across the y-axis. And so we're going to get positive or a negative of that value. And if we were to take those two coordinates, 1 over e and positive or negative 1.6487208, and plug them into our original numerator of our derivative, which we had right here, okay, which was 2xy cubed minus y ln y squared. If we plug those in, right, that just gives us 2 times 1.6487208 cubed over e minus that 1.6487208 times the natural log of 1.6487208 squared. And I'm not going to go and punch that into the calculator, but if you punch that in your calculator, or with the negatives, you'll find out that that does not equal 0, and therefore x equals 1 over e is also a vertical tangent line. So we get two different vertical tangent lines. So if you want to test that out, go ahead, but it's not 0. Alright, our next one here is going to be just finding horizontal tangent lines. So first thing we'll need to do is take a derivative. So we'll start off with our derivative using the product rule on the x squared y, so that's x squared dy dx plus our derivative of x squared is 2x times the y, and then we'll have minus 2y dy dx, and then we'll do another product rule, 3x times 3y squared dy dx plus, that's not a plus sign, plus 3y cubed. And if we gather all the dy dx terms to one side, we'll have dy dx times x squared minus 2y minus 9xy squared. And on the other side, we'll have 3y cubed minus 2xy. And so we end up with dy dx is equal to 3y cubed minus 2xy, all divided by x squared minus 2y minus 9xy squared. And to figure out when this has horizontal tangent lines, we'll just set our numerator of our derivative equal to 0. So 3y cubed minus 2xy is equal to 0. We'll factor out just a y from that. And so we end up with y times 3y squared minus 2x is equal to 0, which gives us that y is equal to 0, or that, we could say 2x is equal to 3y squared, or x is equal to 3y squared over 2, or 3 halves y squared, or however you want to look at it. So y equals 0, if we plug that into your original equation, you just get 0 equals 0. So that's perfectly fine. That's going to be a horizontal tangent line as long as it doesn't make the denominator equal to 0. So when y is 0, the only thing that would make that denominator 0 is if x does not equal 0. So y equals 0 is a horizontal tangent line as long as the x value is not also 0. And then we'll deal with the x equals 3y squared over 2. Well, we need to plug that back into our original equation. So when we plug that back into our original equation, right, we had if x was 3y squared over 2, we started with x squared. So that'll be 9y to the 4th over 4 times another y. So that'll be 9y to the 5th over 4. And then we have the minus y squared that was already there. And then it was equals 3x times y cubed. So that'll be equals 3 times our x, which is 3y squared over 2. So that'll be 9y squared over 2. And then we're multiplying it by the y cubed, right? Because it's y cubed, right? So that'll be 9y to the 5th over 2. And we should then, again, really quickly be able to just solve this down. If I just subtract the 9y to the 5th over 4 to the other side, that's, I have 9 halves y to the 5th minus 9 fourths y to the 5th ought to be 9 fourths y to the 5th. And then we'll have a plus y squared equal to 0. We'll factor out the y squared, which gives us 9 fourths y cubed plus 1 is equal to 0. And we can ignore the y squared equals 0 because we already dealt with that. We already got y equals 0 as 1. So we end up with 9y cubed equals negative 4, or y cubed equals negative 4/9, or y is equal to the cube root of negative 4/9. And so what we should really do here with that is we should plug it back into our original equation. And if we take that cube root of negative 4/9 and plug it back into the original equation, we're going to end up with, in fact, I'll write this on a new page. All right, it was y equals the cube root of negative 4/9, and we're plugging it into our original equation, which was x squared y minus y squared equals 3xy cubed. We've got to confirm that it does give us some actual x values in our original equation. We end up with x squared times the cube root of negative 4/9 minus negative 4/9 to the, well, we're going to cube root it and square it, so that'd be the 2/3 power, is equal to 3x times the cube root of negative 4/9 cubed would be negative 4/9. So we can just graph both of those equations and make sure that they have an intersection point. So we'll do that on our graphing calculator. We'll hit zoom option 6 just to make sure we're back at our standard window. We'll clear out our old equations, and we've got x squared and then times the cube root, which is in the math window, option 4, cube root of negative 4/9. And then we had minus, and then it was negative 4/9 to the power of 2/3. So that was our first equation. And then our second equation was 3x times negative 4/9. So that'd just be negative 4x over 3. If we simplify that down. And if we look and see, looks like they do most likely have an intersection point over here. We second and then calculate the option 5 intersect. looks like they have an intersection point there of 0.8735797. I'm going to zoom in around that point, or at least somewhat close to that point. And it sure looks like there might only just be the one intersection point there, or they just actually happen to be tangent to each other at that point. But regardless, it doesn't really matter as long as there's at least one intersection point that works. That's fine. And the one that we got was x is equal to 0.8735797. And so if I were to take that, this x value and this y value, and just confirm that it doesn't make my denominator here equal to 0, then I would know that this is also a horizontal tangent line. I'm not going to go through the work to just plug those two numbers into the denominator of my derivative. I've done it when I made the answer key. It doesn't yield 0, and so we end up with that as our horizontal tangent line. So we have two of them, y equals 0 and y equals the cube root of negative 4/9. All right, our last couple problems here should be quicker and easier. So we are just going to, first off, look at this one where we have a particle moving along this position equation, tangent of sine of e to the 2t, and we want to find the velocity and the acceleration of it at the first time it is at the origin. So first of all, we need to figure out when it's at the origin. Well, something is at the origin when its position is equal to 0. Its position is the tangent of the sine of e to the 2t. So in order to figure out when that's equal to 0, we'll go back to our standard zoom here. We will clear out our old equations from the previous problem. And we'll just type in the tangent of the sine of e to the power of 2x, since we don't have, we're not doing this with a variable t, we're doing it with a variable x. And make sure your mode is in radians, because otherwise you're going to get a really messed up graph that doesn't work. So this is asking us for the first time it's at the origin. I'm going to zoom in a little bit around 0, 0. The first time it's in the origin is the first time after x equals 0, where it equals 0. So we'll do second trace 0, and we'll just come over here. We're a little to the left of that first x-intercept. We're a little to the right, and we will get this very nice value of 0.5723649. So we know this is true when t is equal to 0.5723649. So that is our velocity, or sorry, that is our time at which the function is at its at the origin. And so then from there, what we need to do is we need to figure out the velocity and the acceleration of it. So the nice thing is that we can just use our calculator and say, well, we want the velocity at, and I'm just going to call this a, so that I don't have to keep rewriting it. The velocity at a is just equal to x prime at a. Okay? So if I do that, in fact, I can even do that on my graphing calculator here. If I go out of here, I can type in that number, which we just had, which I've now forgotten what it was. I believe it was 0.5723649. 0.5723649, yeah. And I can hit the STO arrow button in the bottom left corner here. And if I hit alpha and then A, it'll store that as A. So I don't have to keep typing that number over and over again. So if I go back to my graph and I want to find the derivative of my graph at A, I can just hit second trace. Option 6 is dy dx. So we'll just do option 6. It doesn't look like it does anything. Just type in alpha A, and it will tell you that your derivative there is negative 6.283185. And so we can say that this is equal to negative 6.283185. And then from there, it asks us to find the acceleration also. Well, to find that acceleration, we've got two options. One of them is to actually take the derivative of the position function, find the velocity function, and evaluate it at A. But the other option is kind of a cool trick we can use here. If we go out of this completely and hit Math and say option 8, which is in deriv, which really just pulls up a derivative for you, we can say we want the derivative with respect to x of, and then what we actually want is the second derivative because the acceleration is the second derivative. So if I just do that same thing again and throw another one in there, I can say the derivative of my function, and my function can actually be found. I don't have to retype it, even though it wasn't too horrible to type in. I can hit VARS over by the clear button. If I go to the second column, Y VARS, option 1 is function, and then I can just choose my function. So I can say to find the derivative of my original function first at x, and then evaluate that second derivative of it at a. And if I do that, it should give me negative 12.565989945, which is a much easier way than actually having to go about doing this by hand. And so I can then say that the acceleration at A is equal to the second derivative of the position at A, or the derivative of the velocity at A, and it just comes out to be negative 12.565989945, which might be slightly different than what I have in my answer key, maybe just due to some rounding. The calculator is doing something slightly differently with maybe a new system update. But those are our two answers. All right, and we're on to our last problem here. We got a particle moving according to this equation, sine of 2 to the power of x over 2. And we want to find the acceleration of the particle at the first time when its velocity is equal to 0. So what we first need to do is then find a velocity function. Well, to find the velocity function, that'd be the derivative of the position function. Well, the derivative of sine of u is cosine of u. And then we have to multiply that by the derivative of the u, which is the derivative of 2 to the x over 2. Well, that would be 2 to the x over 2 times the natural log of 2. But then we have to multiply that by the derivative of x over 2, which is 1/2. So we want to know, when does v of t equal 0? Well, v of t equals 0 whenever that function crosses the x-axis. So what we'll do is we'll just go in and we'll graph that function. So we'll go back into our y equals, clear that out, and we'll type in that function. So that function was cosine of 2 to the power of x over 2. And then we're going to multiply that by 2 to the power of x over 2. And then we're going to multiply that by the natural log of 2. And then we're going to multiply that by 1/2. And if I graph that, it looks like that. So I probably should have reset my window, but it looks like the first time it equals 0 is just a little bit more than 1 over there. And so we'll just use second trace. We'll calculate the 0. And all right, I'm a little to the left. I'll hit enter. We'll go a little ways further till we're for sure a bit to the right. Hit enter. Now in guess we'll hit enter again. And it looks like we end up getting 1.3029923. So we'll go back here. We'll say that happens when t is equal to 1.3029923. And we want the acceleration at that point. And since I don't need to use this value more than once, I'm not going to bother to go in and store it in my memory. I'm just going to go ahead and say a of 1.3029923 is equal to v prime of 1.3029923, which is, and then I'll go back to my graph. I'll say second, calculate option 6, which is my dy dx. And we'll just type in 1.3029923, I believe is what it was. And we'll hit enter. And it should give us negative 0.296368. And so that will be our final answer. This is equal to negative 0.296368. And that is our acceleration at the first time when the particle's velocity is 0. So that's the end of our walkthrough for the calculator derivatives homework assignment. Kind of a long one. A lot of steps with the calculator, but the concepts are kind of sort of what we're used to. And that's it.